Morning, I am SIDDHARTH Sharma from Arya College of Engineering and IT from Department of Mechanical Engineering. I am presenting boundary layer equation. These are the content which I will cover, that is nominal thickness, displacement thickness, equation for the displacement thickness, momentum thickness, equation for momentum thickness and continuity equation. Nominal thickness of the boundary layer is defined as the thickness of the zone extending from solid boundary to a point where velocity is 99% of the free stream velocity u. Capital U denotes the free stream velocity, and at the value of its 99%, a thickness is achieved which is called the nominal thickness. This is arbitrary special because the transition from zero velocity at boundary to a u outside the boundary take place. It is based on the fact that beyond this boundary, effect of viscous stresses can be neglected. Other definitions of boundary layer thicknesses. Many other definitions of boundary layer thicknesses has been introduced at a different times and provide important concept based on mathematical calculations and logics. These definitions are displacement thickness, momentum thickness, and energy thicknesses. Displacement thickness. Presence of boundary layer introduces a retardation to the free stream velocity in the neighborhood of the boundary. This causes a decrease in mass flow rate due to presence of boundary layer. A velocity defect, that is capital U minus small u, exists at a distance y along y axis. Displacement thickness may be bought of us as the distance measured perpendicular to the boundary, with which the boundary may be imagined to have been shifted such that the actual flow rate would be the same as that an ideal fluid flowing around the displaced boundary. This may be imagined in as explained in the figure in the next layer. This figure shows the velocity distribution for the displacement boundary layer. These are the equation. By equating the flow rate for velocity defect to flow rate for the ideal flow, delta star b u. Delta star denotes the displacement thickness, b is the width of the boundary layer, capital U is the velocity of free stream, is equal to 0 to infinite, capital U minus small u, b into dy. In this diagram, we can easily see the capital U velocity defect, ideal fluid flow. So velocity defect and equivalent flow rate are shown by the left hand and right hand diagram respectively. Now in our equation, if density is constant, it simplifies to delta star is equal to 0 to infinite 1 minus u small capital U into dy. Now we come to the momentum thickness. Retardation of flow within boundary layer causes a retardation in the momentum flux too. So similar to displacement thickness, the momentum thickness delta is defined as the thickness of imaginary layer in free stream flow which has momentum equal to the deficiency of momentum causes to a actual mass flowing inside the boundary layer. Again, what is momentum thickness? This is the thickness of an imaginary layer in free stream flow which has momentum equal to the deficiency of momentum. There is a free stream boundary layer in which there is a momentum and its momentum is equal to the deficiency of momentum that is caused by the actual mass flowing inside the boundary layer, and this thickness is called the momentum thickness. Equation for the momentum thickness is right as integration rho u capital U minus u dA is equal to rho b 0 to infinite u minus u dy. By solving these equations, we get rho b u square theta is equal to rho b 0 to infinite u minus u dy. Theta is equal to 0 to infinite u by u, that is dy. Here theta is denoted the temperature difference, that is final temperature minus initial temperature. This is the graphical representation of the momentum thickness. We can easily see the thickness delta u is equal to u infinity. At lower side we see the small u. On the y-axis delta star is shown. U infinite is shown by the horizontal line. On the x-axis u by u infinite is equal to 0.99, as we discussed in the definition of the momentum thickness. So this is the graphical representation of the momentum thickness. With the help of this graphical representation, we can easily find the momentum thickness, and we can easily understand the definition of the momentum thickness. Now at last we come to the continuity equation. Only steady two-dimensional flow is considered for simplicity. So continuity equation in 2D is delta u by delta x plus delta y is equal to 0. Because it is the two-dimensional equation, so we will consider only uv. And in this above equation, u and v are the velocity component in x and y axis.